Welcome back. This is an Aleks homework video on solving applied problems with first-order kinetics. Okay, I would call this hard because you've got several different possibilities of things that they could ask you. So they could ask you problems with different concentrations. In case you would use an integrated rate law. I'll write that down in a second. You could use half-life questions, which means you need to know a half-life formula, which I can give you also. To start off, it's first-order kinetics. And first-order kinetics just is the rate of whatever you're either making or is going away. That rate is equal to some constant times the concentration of the stuff that you're looking at. Whether you're making something or you're making something go away, this is first order, which means that this concentration is to the first power. So it's simply the concentration times the rate constant. So not so hard. If you are comparing two concentrations at different times, so you have an original concentration and it's either going away or being produced, and you want to find out what's going on with the concentrations, how fast is it going away or being made, then I would need a formula that has two concentrations in it. And I would use the integrated rate law. Now an integral is a calculus thing, so you don't necessarily have to know calculus. You would simply memorize the rate law, knowing that in a first order kinetics problem, what would the formula that I need to use, and I would use this one. It's the natural log of the concentration of the stuff we're looking at divided by the concentration originally. Now normally this is a molar concentration, moles divided by volume. In this particular question that I'm looking at, it doesn't have molarity, it has atmospheres. So I really can simply use the atmospheres of gas that I have now divided by the atmospheres I would originally have. So it would work just the same. It'd be the natural log of that. And that's going to be equal to negative K, which is my rate constant, times the time in seconds. So this is per second that we're talking about. So I would need to put all times in seconds. If they give you a half-life problem, the half-life is, I'll write it here. So the half-life simply means at what time has half of the stuff disappeared. So you had a concentration, it's going away. At what time in seconds is that half remaining? Okay, so half is gone and half is still there. And this is also a natural log, so its natural log happens to be of 2 divided by the time at the half. Okay, so the half-life is equal, and that's all equal to K. So K equals the natural log of 2 over the time in seconds of that half-life, however much half is still remaining. So it really depends on what you're being asked. Here, I've got two different concentrations. I've got a flask that has 0.14 atmospheres in it, and then 13 hours later it has 0.104 atmospheres in it. So some of it's disappearing, going away, and I want to know the rate of that. So I need to know the initial rate of decomposition. So I'm going to need just my rate law. I need the rate, which is what I'm finding. I need the K, which they didn't give me. And then I need the concentration. Now, the concentration here is just the concentration of X. All right, so it's just going to be, I could simply just recopy this as X and X. Okay, the natural log of X divided by the natural log of X at the initial. And I have to find K, because if I have the rate equals K times the concentration of A, I have to have K. So I'm going to solve for K here, because I know both of these concentrations. I know that X is 0.14, and I know that X at initially is 0.14, and my new concentration is 0.104. So I can easily do that. So this is going to be, so let's solve for x. What do I have to do? I'd have x equals, okay, I have to get rid of the t, so I'm going to do that as a minus, so I want to get rid of the minus too, so I'll get rid of the t, minus t in seconds times the natural log of x. Okay, so well, the natural log of x is my current concentration in atmospheres, so that's 0.104, and then divided that by, let's do it this way, divided by the original. I'm going to take these brackets off. The brackets mean molar concentration, and I don't need that, so I'm just going to say the natural log of 0.104 divided by 0.140. Okay, that's my current and my initial concentration of the gas. And that looks good. Okay, so I fill in, I need time, 13 hours. Okay, so I have to have seconds for this, so 60 times 60, and so I have 46,800 seconds. So I'm going to say K equals negative 1 over 46,800 seconds. Okay, now I need to divide 0.104 divided by 0.140 and then take the natural log. So I have an LN button on my calculator. That's the natural log of whatever. All right, so let me do that now. So I have 0.104 divided by 0.140 equals 0.7428. Now I'm going to take the natural log, okay, and then I'm going to multiply that by -1, okay, divided by 46800. Okay, and I get K equals 6.352 times, I've got a bunch of decimals, 10 to the -6, and my K is going to be over seconds. So this is 6.352 times 10 to the -6 over seconds. And now I'm going to take that K and put it in the rate. Now they want the initial rate. So this A or X needs to be my initial thing. So it's decreasing from 0.14. So that means that my rate is going to equal my K, which is 6.352 times 10 to the -6, times my initial rate, which they have here, or my initial amount, which is 0.140 atmospheres. And this is per second. So I'm going to end up atmospheres per second going away, which is good. And so that'll give me my rate. I'm simply going to multiply 0.140 times 6.352 times 10 to the -6. And I have my rate equals 8.9 times 10 to the -7 atmospheres per second. Okay. Not terrible, but nobody likes it. So I hope you're learning something.